Okay, we're going to take a look at some applications in 3 dimensions. So even though a right angle triangle is a 2D shape, we can often use it to solve problems in 3D. But this means you're going to have to be able to visualize right angle triangles within 3D shapes. So for example, you can see here that I've got a square-based pyramid. And within that square-based pyramid, if I wanted to work out the height of the pyramid from top to bottom, I'd need to visualize like a right angle triangle there. So the right angle that the height makes with the base there. And it's often really helpful if once you've located the right angle triangle that you draw it separately and sort of do your calculations from there. And we'll look at that in the example I'm going to show you. Another way we can look at it, so this is just another example. So here you've got like a 3D sort of wedge, and within that we've got a right angle triangle here. So even though on the diagram that doesn't look like a right angle, if you can visualize it in 3 dimensions, it is, because you've got sort of the height and the base there. So those make a right angle triangle, and this would be the hypotenuse. Okay, so we'll just do one example. The thing is, you need to do a few different ones from the textbook for this because there's so many different shapes that you could be dealing with, but we'll just have a look at this one here. So here we have a plan of a tent that we're trying to set up. So OP is a vertical pole that you need to set up the tent with, and what we want to calculate is the height of that pole. So it's sitting at the very center of the rectangle QRST. So you can see that the yellow rectangle there, that's the base of the tent. So we want this length here. And hopefully you can see that I've got a right angle triangle here. However, the only thing that I know is that that angle is 48 degrees. And in order to use trigonometry, I need at least one more side to help me calculate it. So I'm going to have to do 2 steps for this one. I'm going to have to look for another piece of information. And what I do know is I know that's 5 and that's 12. So that diagonal there, TR, is I can work out using Pythagoras theorem because that's a right angle triangle there, if you can imagine it just laying flat on the floor. So if I redraw that, so I've got that side is 12 and that side is 5, and that's T, S, and R. I can work out that length here, which is actually this. And then because I know that OP is in the center, I can use half of that to have the side of that triangle that I need. Okay, so for this one, we just need to use Pythagoras theorem because we know the length of the 2 sides. So we know that TR squared is going to be equal to 12 squared plus 5 squared. So that gives me 144 plus 25, or 169. And then to work out TR on its own, I take the square root of 169. So that gives me a length of 13 meters. Okay, so from T to R is 13 meters. So that means that from T to O is half of that, 6.5 meters. So now I can use that to work this out. And again, I'm going to redraw now triangle TPO. So what I know is that from T to O is 6.5, and I know that angle T is 48 degrees. And what I want to find is OP. So OP is the opposite side, and TO is the adjacent. So I'm going to use the tan ratio here. So tan of 48 is equal to the opposite side over the adjacent. So working that out, I do 6.5 times tan of 48. And putting that in my calculator to 2 decimal places, I get that O is 7.22 meters. Okay, so that means that the height of the pole OP is 7.22 meters. Okay, so go ahead and now give exercise 4.3 a go. Again, like I said, please try and do as many of these as you can because it's really important that you're able to visualize the triangles in different 3D shapes.